This is Properties of Radicals, Part 1. A radical expression is any expression with a radical sign in it. So here we have our radical sign. So the square root of 25x to the 5th power is considered a radical expression. For a radical expression to be in simplest form, the following conditions must be met. The radicand, which is this part under our radical sign, can't have any perfect powers. So 25 can be perfectly squared. It's a perfect square. So this would not be in simplest form. The radicand can't contain any fractions. So we can't have any fractions that are completely under this radical sign. And no radicals can appear in the denominator of a fraction. So if we have something in fraction form, it's allowable as long as this radical sign is not over anything in the denominator. It doesn't include anything in the denominator of the fraction. So this guy in simplest form would be 5x squared times the square root of x. So let's see how we get a radical expression in simplest form. The first thing we're going to look at is the product property of square roots. This basically says that if we're trying to find the square root of a larger number, so say we're trying to find the square root of 45, we can break that into 9 times 5. So it's the square root of 9 times 5. That's equal to the square root of 9 times the square root of 5. Since the square root of 9 is a perfect square, this can become 3 times square root 5. Basically what we're saying algebraically is if you're square rooting two numbers that are being multiplied together, you can find their square roots independently as long as a and b are greater than or equal to the number 0. We can't have square roots of negative numbers. So let's apply this property to a couple problems here. So here we're being asked to find the square root of 108, and we want to simplify this, and 108 is not a perfect square. So in order to help yourself out a little bit, I suggest making a factor tree for 108. So I know that I can break 108 into 12 times 9. 12 will break up into 4 times 3, and 3 is my first prime, and 4 can become 2 and 2. Now 9 can break it down into 3 times 3. So I've got 2 times 2 times 3 times 3 times 3 for my prime factorization of 108. Now this helps me out because I want things that can be squared. So I see I have 2 times 2, so that number, and 3 times 3 can be turned into perfect squares that fit under the 108. So basically I'm going to break this down into 4 times 9 times 3. I get the 4 from the 2 times 2, the 9 from the 3 times 3, and then I have this leftover 3 that I can't really do anything with. So this could break down into the square root of 4 times the square root of 9 times the square root of 3. Square root of 4 and square root of 9 are perfect squares. There's nothing I can do about this square root 3. He's kind of a leftover. So I get 6 times the square root of 3 for my square root of 108 simplified. Let's try one here with a variable in it. So I can break this guy up into the square root of 9, which I know is a perfect square, and I can do x squared times x. So I had x cubed, so I wanted 1 squared, because that'll be a perfect square, and then I have an x left over. So this becomes square root of 9 times square root of x squared times square root of x. So this is 3. The square root of x squared is just x times the square root of x. So 3x times square root x is my simplified version of the square root of 9x cubed. I can also look at the quotient property of square roots, which says that the square root of quotients equals the quotient of the square roots of your numerator and your denominator. So the square root of 3/4 can become the square root of 3 in my numerator over the square root of 4 in my denominator. Since square root of 4 is a perfect square, I get square root 3 over 2. This is allowable as long as the denominator is not part of any radical expression. And since it's just regular 2, that's okay. So basically, algebraically, we're saying if we have the square root of a fraction, we can do our numerator and denominator separately. A has to be greater than or equal to 0. B has to be greater than 0 because we can't have a denominator of 0. So let's try simplifying some radical expressions using the quotient property. So in this case, I would look at my numerator and my denominator separately. So square root of 15 for my numerator, square root of 64 for my denominator, and since square root of 64 is a perfect square, there is my simplified fraction here. This time I'm looking at square root 81 as my numerator, and the square root of x squared is my denominator. Both of these are perfect squares. I get 9 over x. So all of these rules can be applied to cube roots. The only thing we have to remember with cube roots is we are allowed to have a negative number under our radical sign because cube roots can be negative. So when you're multiplying a number 3 times, you can have a positive or negative answer. So it's okay that we're looking for the cube root of 128 for that first problem. So in order to do this, what I'm going to probably do first is find my prime factorization of 128. So 128 can be broken into 4 and 32. 4 can be broken into 2 times 2. 32 can become 4 times 8. And once again, 4 is 2 and 2. 8 can become 4 and 2. There's a 2. And 4 can become 2 and 2. So for my prime factorization, I have a lot of 2's. So I get 7 2's there. So I'm trying to find cube roots. So I want 3 of something. So I have 2 sets of 3 2's, and I've got this one left over too. So basically, what I'm going to break this down into is the cube root, and I have to have 1 is going to be negative, negative 8 times 8 times 2. So I'm doing 2 times 2 times 2 to get my 8, 2 times 2 times 2 to get my other 8, and then I have this leftover 2. And since it had a negative answer, I made one of my possibilities here negative. So I'm going to, cube root. So I'm going to do the cube root of negative 8 times the cube root of positive 8 times the cube root of 2. Just becomes negative 2 times 2 times cube root of 2. So this becomes negative 4 times the cube root of 2 for my final answer. Okay, let's take a look at another one. 125 is actually a perfect cube because 5 times 5 times 5 gives us 125. You could always make a factor tree if you need to, but I'm going to break this into 125 times x to the third times x to the third times x. So basically, I'm making sure that my x's still add up to the 7, but I know x cubed will be a perfect cube root. So the cube root of 125 times the cube root of x cubed times the cube root of x cubed times the cube root of x. So I get 5 times x times the cube root of x. So I have 5x squared times the cube root of x. Let's take a look at this guy. I'm going to break this one into the cube root of y on top and the cube root of 216 on the bottom. Now, the cube root of y is not going to be able to be simplified, but I can simplify my 216 because 216 is 6 times 6 times 6. So I'm going to have, for my final answer here, cube root of y over 6. And if you don't automatically know that, you can always make a factor tree for yourself. All right, let's take a look at this last one. So I'm going to break up my numerator into 8 times x cubed times x. 8 is a perfect cube. I'm making x to the 3rd power, which will be a perfect cube, and I have a leftover x. And the cube root of 27 times y cubed. So I can simplify some things here. I'm going to make cube root of 8 times the cube root of x to the 3rd power times the cube root of x over the cube root of 27 times the cube root of y to the 3rd power. So on top, I'm going to have 2 times x times the cube root of x. And on the bottom, I'm going to have 3 times y, which I can't simplify any further. So there is my simplified radical expression.